Hi everybody, welcome back. So last time we got started with learning how to graphically solve things. This time we're going to go a little bit further with that. We're going to try a different example. For example, let's say that you get some resistor and you were trying to calibrate it. What's the resistance? Well, you would do this with the trend line, honestly, but we don't have trend lines yet. We don't know what those are yet. And so we're just going to use this data, which is extremely clean. There's no issues in it. And so what I have is the current and the voltage. Okay? And I've measured those. And I have this relationship over here that says, well, voltage is equal to current times resistance. V equals IR. You might have seen this before, maybe you haven't. If you go into electrical engineering, you'll see it a lot. Until they tell you it's wrong. There's actually a whole lot of corrections to this. But then we can solve and say, well, resistance then is equal to voltage divided by current up, divided by slope. So I look at this, and I want to figure out the slope. Now, this data has no error. It's perfect. And so honestly, I can pick any 2 points and figure out the slope. In reality, you would want to use all the points by fitting a trend line and using the slope from that. Don't know how to do that yet, so just pick any 2 points, take the difference, and figure out this rise over the run. If I do that, well, I rose by 67 volts over 1.34 amps. If I divide those, and it's 50 ohms. If you're wondering, like, why 50 ohms? You did 50 watts, you're doing 50 ohms, 50 everything. You're being lazy. 50 ohm resistors are actually pretty common. So don't judge me too much, okay? And so we can use this to find important physical properties, because you might have a new wire and not know its resistance. From this, you can figure it out. Okay, another important physical property is the modulus of elasticity. Now, you don't really need to use this. This class will never require it. It's if you get to my solid mechanics class, then it becomes incredibly important. But you're a ways away from there probably. But coming back to it, what it is it says if I stretch something, if I pull on something with a certain amount of force, how much does it stretch? Does it stretch a lot? Does it stretch a little bit? The larger that number for your modular elasticity, the less it will stretch. And so how do you figure it out? Well, use this equation right here, which is actually called, I actually forgot for a second. It'll come to me eventually. Stress and strain are related. Hooke's law, goodness. Hate when that happens. Okay, so stress, which is force normalized by the area you're pulling it over, it's more or less pressure, is equal to the modulus elasticity. How stiff are you? How hard is it to stretch you? Times the strain, which is just how much did you elongate, but also you divide that by how long you were originally, because if you elongate by 1 inch and you're 15 miles long, that's not all that much. If you elongate by 1 inch and you're a foot long, that's quite a bit. So depending on how long you were originally, depends on how much it changes. Okay, with that in mind, I have my stress, which is in gigapascals. It's a very big number. And strain, which is in meter per meter, you're like, wait, doesn't that just cancel? It does. It's actually unitless. And I can figure that out. So once again, if you want to solve modular elasticity, that would be stress divided by strain. And if I divide that, work out the numbers really hard, I get 200. And you're good. This is actually correct for steel. For structural steel, not for stainless. Okay, so with that, you've gotten some ideas about how you can use plots of data to solve problems. I'd really love to go into this some more, especially when you get to calculus. There's a lot more to do here. If I have time, maybe during the next problem session, we can go over some extra details about how you can solve problems numerically using plots. We'll get there, hopefully. Okay, now the last one, I'm going to explain it to you, but I'm going to make it you do it on your own, because you got like 4 questions here that you need to answer. Okay. So what I have here is the velocity of 2 cars, car A and car B. And they're in a race. They're in the 24 hours of lemons, which lasted 50 seconds. So maybe both cars just died. If you don't know what 24 hours of lemons are, look it up. It's absolutely hilarious and amazing. Okay, so I got these 2 cars. I have their velocity as a function of time. Now I can look over here and I see that velocity is change in position over change in time. The faster you go, the further you go. And I also can realize that acceleration is how quickly your velocity can change. Okay, So if I solve both of these, I see if I take the area under the curve, I get how far they went. And if I take the slope of the line, I get their acceleration at that point. So if it's flat, they're not accelerating, their velocity is constant. Acceleration is 0. If it's going down, their acceleration is negative, they're slowing down. If it's going up, their velocity is increasing, they're accelerating, the acceleration is positive. If I take the area under this big curve from between any 2 points, I know how far they went during that time. So if I go from the beginning to the end, I can figure out how far they went and who went further, who won. So with that in mind, try it. Use what we did. There's lots of difficulties here. Break it up into triangles, okay? Break it up into triangles. If you get it wrong, just as a note, 2. Boop. It will walk you through the first 2 of these. The rest you have to do on your own. And also, there's only 2 possibilities. It's not like you can really get it wrong, but I want you to try to do it because this will help you later on. Okay, with this, we've had some fun with graphical solutions. Hopefully this makes sense. This last example, it's also in the PowerPoint, which I attached with this unit. It's an older PowerPoint, but it has examples that are very similar to this that can help you get through it. So use those to your benefit. And also, figuring out the area of this big shape is difficult, but figuring out the area of a bunch of triangles and squares, much easier. Use that to help you. I'll see you later. Bye-bye.